very much. So let's get into it. So the framing of the talk will be, I think, the framing of this workshop in some degree. How do we enable foundational innovation for robotics and particularly self-driving research, autonomous vehicles? And I'll start out with this, I think maybe not controversial claim for this audience here, but just like we've seen this transformational power of big data for language, we want to apply it to a more grounded setup where we have sensor data that a robot will see. And I actually feel like in terms of scale, autonomous vehicles might be one of our best shots at collecting large scale, what I would call 4D data. So we can get sensors that capture 3D, but over time, so we get this fourth dimension. And the claim is just like we're trying to, we've seen incredibly emergent behavior just by doing next word prediction for language. Maybe we'll see a similar kind of foundational innovation for doing next LiDAR prediction. Okay, so in some sense, what I'll advocate is a view of learning from spatiotemporal data that will make four-dimensional structure first-class citizens. The fundamental thesis is that if we're going to move and navigate and operate in a physical world, then having the 3D structure and technically 4D structure of 3D plus time should be explicit. Okay, so the setup we're going to do is look, okay, can we try it as a thought experiment? We'll try to make this a bit formal. Let's try to replicate the innovation we've seen for language in sensor data that autonomous vehicles would collect. And at first glance, this is a very reasonable kind of statement. So it's really well known that just like in any data set collection endeavor, typically you're swamped with data and you can only label a tiny fraction of it. So even by modest accounts of the largest scale fleet and capture, such as that data collected either from Waymo or from Tesla that probably have the largest footprint, only a tiny fraction of it will ever be labeled by humans. And so this suggests that hopefully we can see the same kind of innovative impact if we're able to self-supervise from this data. Okay, so if we want to set up a self-supervised task that's sort of analogous to what word prediction is doing, we might do something like this. And in fact, this task has been proposed before, which is next LiDAR frame prediction. So you can imagine we're going to train a network given previous, let's say, T steps of LiDAR. It predicts the next frame of LiDAR or the next T frames of LiDAR. And the reason why this is self-supervised is we can compare that prediction just by, we can just let time evolve forward. We can see how the world actually looked in the future and compute some squared error between the two. And now train a model that will try to predict this. And hopefully, if a model can do well at this, and because it doesn't require any explicit labels, we can train this at scale. And hopefully the model can do well at this, that will learn to structure will emerge about how objects move and behave. And hopefully at an emergent scale of the things that we see with large language models and even video models like Sora. Okay, the first thing I want to call out is that actually there's a difficulty, if you, and previous work has done this, but there's a difficulty in doing this, and that is 3D sensor data points are a little bit subtle to work with. And in particular, the points that are sensed, if you just think about the physical process, there's a ray that shoots out from the LiDAR sensor and it hits the physical structure in the world. And so one way to think about this is imagine the world is not changing. There's nothing actually happening, but my car is driving down the road. It's very clear that it will look like points are moving, but in reality, of course, nothing is changing in the scene, only the sensor is. So the problem with if you just try to naively predict a point cloud from a LiDAR sensor is what you're really asking the model to do is predict properties of the sensor, which is how many beams do I have, how is the sensor moving over time. But what we really want to understand is the world. That is the fundamental thesis that we make. If we understand spatiotemporally how the world is evolving, then we can safely navigate. Okay. And so it turns out there's actually a fairly simple way of modifying this, which is instead of asking a network to predict point clouds, we ask this network to predict something like a 4D occupancy field. So one way to think about this is we just grid up the world into X, Y, Z in time, it's four-dimensional. And for every voxel in the grid, we predict, is there something there or not? It can be a number between 0 and 1. So we can think about this as almost like, if you're familiar with the literature on NERFs, it's an occupancy field, and this is an explicit occupancy field. If you wanted to, you could break the parameters of a NERF that would be an implicit occupancy field. But now the trick that we're going to do now is, given the occupancy field, we will use known sensor extrinsics and intrinsics in the future. Because we know how the car actually moved in the future, we can now render this field from particular sensor positions. And what we get out is a rendered LiDAR sweep. And this is pretty easy to do. This is exactly what you do in NERF. You shoot out rays and you see how the rays intersect your occupancy field. And now, instead of rendering an image, we render a LiDAR sweep. And now we can compare the sweep with the ground truth. And so what we find is that this is actually a pretty nice way of trying to have occupancy 4D structure emerge. So what I'm showing here is the ground truth feature. These are two prior work models that actually suggested point cloud forecasting as a task. And in fact, what I'm showing here is a dumb, apologies for the ignorant statement, is a naive baseline that all it does is it just takes all the points that you've seen already, and it just, how do I say this? Baseline where we take the points that we've seen already, and we just use the, we use the knowledge of where we're going to be to just show those points. And so this is actually, there's no learning involved. We just take all the collection of points that we've seen. And now when we shoot out rays, okay, now I remember what we do. Sorry, it's a brain freeze for a second. When we shoot out rays about where the car should be, we'll just take the closest known point that we've seen before. So the way to think about this ray tracing baseline is just assuming the world is rigid. I take all the points that I've seen before, put them into a big point cloud. I know how I'm moving, and so I'm going to shoot out a ray, and I'm just going to grab, I'm going to say, where do I think is the closest point that it's going to hit? So this requires no learning. And this already, if you actually look at the predictive accuracy of this model, it outperforms these learning-based solutions. What we're going to do is something I think a little bit better. We're actually going to predict 4D occupancy, and then we're going to differentiably render the same way you would with an Earth. Okay. And so what's kind of cool about this is that although we've never trained this on any 3D data, we just trained this on LiDAR sweeps, which is point clouds, 3D structure emerges. And it almost has to, because we're sort of hypothesizing 3D structure such that when we raycast it, it looks like the actual sweeps that we think. And so one of the fun things you can do with this kind of 4D model is that you can render it not just from your actual LiDAR intrinsics, but you can render it from a different LiDAR. You can say, well, instead of throwing out 32 beams, let me throw out 16. And you can render what a different platform, a different LiDAR that you would have seen. And so as far as I know, this is what this allows you to do is train on one kind of LiDAR data and test on another. And I guess one philosophy here is, I'm sort of stealing a quote from Judea Pearl, who's one of the godfathers of causality. I had the good fortune of working with him on a grant, and he made this statement that always stuck with me. He said, we should make a commitment to modeling the world and not the data. And so I think that's what this philosophy is. If we just try to predict points, we're really trying to predict properties of the sensor. But in reality, we should really try to understand the world. The world is 4D, it's volumetric. It's undeniable. There's structure, and that structure is changing. And if we make a commitment to model that, we can abstract away the properties of the sensor. So I also believe this would allow for cross data set learning, which is something that, like I said, you could train on one kind of platform, test on another, or maybe you can even train on different platforms. That's probably the more compelling version of this. That we know that training at scale is always this huge enabling sort of property. And so being able to take different kinds of LiDAR and train a coherent 4D model of how the world evolves. I should mention that we've actually held a benchmark competition on this 4D occupancy forecasting at another workshop yesterday. There was a whole bunch of entries and results. And so I think this is a nice way to kind of formalize this task. We can benchmark it without any labeling, and we can train it without any labeling just by using points. The important thing that you need to know is you need to have point clouds that are also posed. But importantly, we have that for autonomous vehicle data sets because almost all poses are always aligned to a global map. So I think this fits in really well for this differentiable pose perspective. Okay, and then so some thoughts that we've kind of entertained is if you understand volumetrically how the world is evolving in the future, maybe you can use this as a cost map for motion planning. So you can then hypothesize different plans for how the ego agent can move, and you try to pick a plan that does not go into any occupied space. And although this by itself, obviously this has no knowledge of semantics. It doesn't understand what the traffic light state of the world is. It doesn't really know if one of these bumps is a person that's moving or a car. But at a first order approximation, it should, this does reveal what the model thinks geometrically where stuff will be in the future. And I think the higher order bit, like that's how we should safely navigate. We should move to places where things, where there's free space. Skip that for the moment. And now we'll talk about some extensions we've done on this. That was just a model where we don't explicitly model moving objects separately from static objects. But the other kind of overwhelming philosophy we see here with this kind of at scale automotive data is that it's also undeniable that 90% of the world is stationary. And then some bits are moving. And of course, the moving bits are the most important, but so much of the world is stationary. Let's actually perhaps build a compositional model. So what I'm showing here is some work we've done where we've taken LiDAR point clouds and actually build a model of the static background and moving objects, all without any supervision, just by taking the raw point cloud data. I'll sort of talk about how we do this. And I guess the take-home message is we can basically do the same differentiable optimization again. For the moment, pretend we have initial guesses at poses of the ego sensor and also initial guesses of all the poses of all the moving objects. And now what we're going to try to do is we're going to hypothesize geometry of the rigid world, geometry of moving objects, and motion of the object, such that when we hypothesize them and we know where the ego car is, we then render a sweep. We raycast out rays. We see where the intersection is geometry. And then we look at the rendered sweeps versus the actual sweeps, and we use that signal to drive better models of geometry and motion. And when I'm showing examples here, this is simply doing differentiable rendering on this kind of 4D data. And to actually get this right, I'll show off what I think is a cool but underappreciated property of LiDAR, which is even though almost every LiDAR sweep that has ever been visualized looks like this on the left-hand side, we show a 360 sweep. That is not how the sensor works. The sensor is a revolving sensor. It's a revolving continuous time sensor. And it actually takes roughly 100 milliseconds to sweep all around. And so importantly, what's happening is during the 100 milliseconds, the world's changing. The sensor is moving and then the world is moving. And actually, if you don't model that, that causes incredible amounts of headaches. But it turns out it's actually not that hard to model correctly. So I'll show some examples here. So imagine, so what I'm showing here is the ego car is actually moving that way, moving in this direction. There's another car that's on the world that's moving opposite to that. And you can imagine that basically any sweep that's ever been shown, what a sweep actually is, it's a virtual rendering. You take all the points that were collected from this 100 milliseconds of time, and you say, where would they have been if I had been at if my sensor wasn't moving? So every sweep that you actually ever see is a virtual fabrication. And what that means is every sweep that you ever see has a seam in it. And on one side of the seam were points collected at t is equal to 0. On the other side of the seam were points collected at t is equal to 100, because it took 100 milliseconds to move all the way around. And if you get unlucky, like what we do with this car here, you actually see a person in the car twice, at the beginning of the sweep and at the end of the sweep. So now, if you naively model the sweep as the static measurement, the static shutter, and you try to fit geometry, these 3D or 4D models to it, you bet you fit bad geometry, because you think there's two people in that car, when in fact there's one. In fact, there's other problems that appear as well. So imagine you're driving fast through a corner, and as you're driving, your LiDAR sweep is turning. And what this means is, it could be that by the time you get to this position, you actually see this point on the other side of the building. But now, if you abstract this as a virtual sweep, as everyone does, that was seen from this position, what ends up happening is you end up seeing points behind other objects. And so this causes enormous confusion in the literature. And you'll see lots of papers that try to do various filtering and image processing attempts to try to clean up the data. But my claim is the data is not noisy. It makes total perfect sense if you just model it correctly. And so the solution is we just optimize our neural reconstructions over continuous time. Instead of treating a sweep as a 360 measurement, we treat each slice as a unique measurement. And then we say, where exactly was the car when the sensor was pointed 0 degrees? Where exactly was the car was the sensor pointed at 10 degrees? So in fact, this, by optimizing for, what we can do is we can take the original annotations, ground truth annotations that exist in this analytical data sets like UCs. And if you just naively try to take all the points from different time steps for a moving car, align them, and then fit a surface to them, you get really really poor reconstructions. If you now optimize for the position of this moving car at every time step, so as to minimize reconstruction error of rendered points versus the measured points, you get a much cleaner looking car. And now, if you actually model the fact that it's a rolling shutter, you optimize for the very precise ego motion of the car at different time steps within a sweep, you get a much more high accuracy model. So that's what I claim here is that all this machinery for differential rendering with raycasting, it works beautifully for LiDAR. And it works beautifully for continuous time measurements. Because we just throw out rays at different points in time. We don't have to abstract this as a sweep. And I should say that we have a paper in doing this that's coming out on archive, and there's also a paper in this conference, NewRad, that does this. And so I think this is, as far as I can tell, this is it's kind of a no-brainer. This is the right way we should be modeling LiDAR data. And one of the things that I showed is that what's interesting is that basically the claim is that you can use this machinery to improve upon ground truth annotation that is provided in these data sets. So in fact, if you take ground truth tracks, these are the reconstructions that you see. And in fact, up here, let's show it over here. This is actually the reconstruction of the world. You take the ground truth background points and align them based on the provided ego poses. So basically, one of the claims here is that we shouldn't actually trust the ground truth that's provided. And in some sense, we should use these kinds of space-time reconstruction optimizations to produce the ground truth. And if we do that, the kind of fun thing is that we actually don't need as much ground truth. So we do this experiment where maybe you only assume labels are provided for moving objects every 1 second or every 2 seconds. Or no labels are provided at all. You just run off-the-shelf detector and tracker. It turns out that does produce the same accuracy as if you had these sparsely labeled sequences. So what this is suggesting is that we can actually do this space-time decomposition of compositional objects on unsupervised LiDAR sweeps. So this is what we're trying to do now, sort of do this at scale. And the claim is like, this is one way of building sort of foundational 4D knowledge. Instead of just predicting points in the next time sweep, we can actually fit exactly how all the dynamic movers are moving and try to predict that information. Okay, so this was all about trying to do 4D reconstruction from LiDAR sweeps, but you can also ask the question, can you do this from RGB images? So let's say you're not Waymo, you're Tesla. And so you have very famously not a LiDAR sensor, but you have lots of RGB sensors. And so we've done a fair amount of work of trying to do 4D reconstructions just from RGB data. And a graduated student, Geng Yang, who's put a lot of effort into producing sort of open source code for doing this. Our hope, and we haven't done this yet, is to sort of make this a version of Nerve Studio for dynamic scenes. But it's actively maintained, and so you're going to try this kind of code out on your own RGB sensor data collected from moving cars or moving vehicles, or even from handheld RGB views. You can go ahead and try this here. So I wanted to show off like a fun visual of what you can do. So talked about reconstructing 4D reconstructions of dynamic scenes from LiDAR, trying to do this for RGB. And then, of course, what we really have on an autonomous vehicle stack, we have multimodal sensor data. So another example of multimodal sensors is actually, I think we all have them in our back pockets. Your cell phone has a LiDAR sensor, mine does, it has 3 different cameras. And it turns out if you take videos from this, you can also apply the same 4D reconstruction techniques that I talked about. We hypothesize rigid backgrounds, we hypothesize poses of moving objects and poses of the cameras. Given all those hypotheses, we render an image and we render a depth map and compare it to the measured image and the measured depth map. And once we do this, we can actually get reconstructions of dynamic scenes with much higher fidelity because RGB gives us a much higher res signal than the depth. And we can do some kind of cute things. Normally in the world of 4D reconstruction and neuroview synthesis, you kind of render things from random viewpoints. What you can do here is just something advantage. We can render from a bird's eye view. This is an indoor scene, obviously. But we can also, because we've reconstructed the motion of, in this case, a cat, we can put a virtual camera on the front of the cat's face and render the world from the cat's point of view, which is kind of fun. We can also put a virtual camera right behind the cat, this blue camera. And because this is collected from a sensor stream of video data that was collected, this is the grad student in his home and his pet cat, we can show the renderings over time. So from this single video stream, the single video plus LiDAR stream, you can fit 4D models and then you can then re-render. And so this is seeing exactly what the cat sees. And this is this little, this sort of blue camera that's following the cat as it moves around. So these are fun examples of showing such reconstructions for other sort of dynamic scenes. So there's just one to show us. I wanted to show these off. So the take-home message here is that I think by fitting 4D models of the background, the rigid background plus dynamic objects, I think this will allow us to learn foundational knowledge that can then allow us to then safely navigate from a robotics perspective. And let me sort of throw out 3 possibilities for these 4D models. So one is use these reconstructions as almost simulators for validation. Very famously, it has been said that in order to bring the safety critical technologies such as self-driving to fruition, we need to validate on 1 trillion miles of data. And right now, no one is close to getting 1 trillion miles from a fleet. And so that suggests we really need to have simulation as part of our validation stack. So maybe we can build models of cities and moving cars by using these kinds of techniques that are emphasized here. The other place where you can use these kinds of 4D models is to train. So once all the fitting, the differentiable optimization that I'm talking about is very expensive. And so you can never run that on a car, but you can imagine doing this on offline data and this very expensive test and optimization, and then take those predictions and then train a fast feed-forward model. This will actually predict deformations of people and cars in a feed-forward way. But the third thing I wanted to talk about, the time that I've left, is using these kinds of simulated models of dynamics to help actually plan for controlling the vehicle. Is Kosher?
Yeah, he's online.
Okay, all right, cool. So Kosher will leverage your work quite a lot in this. So the thing I want to emphasize here is new plans. If you folks don't know about it, you definitely should. I think it's a pretty remarkable achievement in kind of taking real world data from an autonomous vehicle fleet and turning it into a full-fledged simulator where you can actually evaluate planning algorithms. So what I wanted to do was talk about it a little bit in a recent method that we have for using these 4D models of how the world can evolve to help better plan. Okay, so first, because people may or may not know about this, but so this data is fairly large scale, 1,300 hours and 50,000 longs collected across different cities, Pittsburgh, Boston, Singapore, and Las Vegas, across different types of scenarios. what we're visualizing here are 6 out of these 80. And what this does is, this data is set up as an interactive planner. And as far as I can tell, this is, if anyone else knows of others, please correct me. But usually when we evaluate planning algorithms, we have to go all the way to simulation. So Chelsea was talking about this in a previous talk. So in the AV world, it would be Carla. As far as I can tell, this is the first data-driven simulator for evaluating autonomous vehicle stack, at least the planning portion of it. And so what I wanted to talk about was even evaluating a full planner is kind of tricky. The simplest thing you can do, what this benchmark proposes, is once I finish introducing it, I'll show you what I think are state-of-the-art results on it. But what this benchmark proposes are 3 different ways of evaluation. So if you have a planner for a robot autonomy, the simplest thing you can do is, if you have recorded logs of how the robot moves in this dynamic world, you could give them the past 2 seconds, give this task to a planner that says, plan out where you want this autonomous vehicle to be for the next 8 seconds. And you can simply look at the squared error between where the planner says the vehicle should be and where the vehicle actually was in the future. So this is called open loop evaluation of the ego vehicle and open loop evaluation of other agents, meaning the rest of the world just evolves as it does in the recorded data. What I claim is this is essentially like a forecasting metric that's done for the ego vehicle as opposed to other agents. The next most sophisticated way of evaluation, actually, the next most sophisticated way of evaluation is whenever you evaluate this forecaster, instead of always using ground truth histories, importantly, you let the ego vehicle execute its plan, and sometimes it might plan to go off the actual trajectory it was on, and it might end up over here. And so now what you do is you query it with the actual history of where it's been for the past 1 second, and you still ask it to plan where it is in the future. But importantly, the rest of the world still evolves on a rail. The rest of the world still moves as it did the recorded data. And so that's called closed loop ego simulation, but then open loop agent simulation. But the holy grail of evaluation is that the ego agent can move off its path that was recorded in the data, and other agents will now react to how the ego agent is moving differently. So now you have to endow other agents with reactive logic. And so importantly for this benchmark, this first wave evaluation, you can evaluate just with squared error. Your planner says, I want the car to be over here. The car was actually here. And so you look at the squared error. In these other cases, you actually evaluate this as a simulator where you see, okay, I'm trying to get to my goal state, and either the other agents are on a rail, they just do what was recorded, or they can react to what I'm doing. But then the way I evaluate success is how close did I get to my goal position? Did I run into anyone? Did I was I uncomfortable by doing high acceleration movements, etc. And importantly, in order to make this thing work, what's really complicated is you have to, this last bit on the bottom right-hand side, you have to make agents reactive to, it's almost as if you can joystick control a planner. The way to think about this is you can move the ego car any way you want. And now the rest of the world reacts to how you're moving. And that's what this third option is. You can evaluate a human planner, just letting him play this as a game. Okay, but now what's super important is, well, how does the rest of the world react? And folks may or may not know this, but that's a whole difficult challenge in of itself. But a simple way of handling this is something called an intelligent driver model, which is essentially is dialed with very simple logic. I'm showing you all the code here. It's 10 lines of Python code that basically makes other vehicles behave like adaptive cruise control. They will still move along their rigid path. But if there's any other car that comes in front, they're going to put the brakes on so they don't run into stuff. This is what your adaptive cruise control does. So this can be done in 10 lines of Python code. It's not so difficult. You have a target velocity and you have a min gap you want to maintain. You might even see this in your cruise control, how close you're willing to get to the car in front. And you do all this, and there's very simple logic that updates your velocities. Okay, and so this is actually the smart logic that's in these other cars. And now, now that you have this, a very attractive way of doing control, and what I saw in the software industry is essentially trajectory optimization via model predictive control. So what this means is if you're, the way the planner operates is, I'm at a time instant, I've observed the last 2 seconds, I'm trying to plan out the next 8 seconds. I'm going to unroll in my internal head how I think the world will evolve. I think other things are going to move in a certain way. Based upon that, I'm going to try to find the best trajectory I can move that minimizes some loss, make sure I don't collide into anything, and maintains comfort and progress toward goal. So this is called trajectory optimization. It's on-the-fly optimization of an internal world model that's unrolled. You can think about this as something like, this is what AlphaGo does. If you're trying to unroll possible moves and say across all those moves, what is the best one I should do? Okay, so this is how I think a lot of autonomy stacks, in particular, classic planners operate. In fact, there was a really incredible piece of work by Poshik that showed that for this planning task, very classic, actually running the IDM logic that we use for other agents, running that as the planner for the Ego agent is very simple, essentially 10 lines of code, outperforms all learning-based solutions. So people try Lang GCN, Urban Driver, and actually I should be that right. So IDM actually is what I just said. IDM performs really well. That performs all the other learning-based solutions. And then Koster had this wonderful piece of work that said we can actually improve upon IDM. And in fact, what the improvement was actually you actually refine what I'm saying. It was this actually. My claim is, and I don't know if Koster would agree, but we should think about this as model and control. Instead of actually running simple IDM logic for the Ego vehicle, what you do is you try to unroll the world forward for 8 seconds, and you want to unroll the world forward in such a way where you predict what everyone else is doing. And then I'm going to evaluate different IDM policies for myself. I'm going to have different target velocities and different mid-gap distances. And I'll see which one of those, when I enroll myself in the next 8 seconds, minimizes a loss. Make sure I don't hit things. Importantly, this has no learning involved. And so this does beat everything else. Okay. So this was kind of, I think, a very frustrating and surprising fact. And I think this is one of the reasons why that, at least for deployed planning, we haven't really seen sort of learning take over. I think there's a lot of learning in early parts of the robot stacks during perception, but for planning, we still have these classic model control methods. So what I'll show is some work that Arun's been doing. It's in the back of this room here that actually shows that you can beat this using a bit of learning, and it's actually leading into this model as a control story. So the solution is, or the observation is that if you actually look at how people behave in different places, let's say you actually look at how agents in recorded data, what is the typical mid-gap distance that Pittsburgh drivers give to their lead vehicle? And what we find is that it differs per city. So in Boston, people tend to drive a bit more aggressively. They have a slower min-gap to the lead vehicle. And this idea that people have different behaviors in different locations is not novel at all. In fact, there's a very well-known in Pittsburgh and CMU, something called the Pittsburgh left. If anyone here is from Pittsburgh. So what happens is if you go to an intersection, what other cars will do is, if someone's trying to take a protected left turn, for whatever reason, it's customary that when the light turns green, you let the first person who's waiting to take an unprotected left go. And if you're not from Pittsburgh, this is really unsettling. All of a sudden, it seems like someone's going to run into you. So the argument I'm trying to make is that there are very, cultural varying behaviors, and you actually see it in the data. Here, there's just this one based on min-gap distance. Certain, for whatever reason, the running theme is going to be Boston likes to tailgate. They have a smaller mid-gap. And so what that means is, what we can do is, when we try to simulate the behavior of other agents, we can actually optimize for these different parameters in my IDM controller, so as to make sure that when these other agents move with this control logic, their final movement looks like the actual movement in the recorded data. So what I'm doing here is I'm actually trying to fit a better simulator for all the other agents. And I can do it per city. And what you find is that in Boston, you try to fit smaller min gaps for your IDM. So Boston drivers should be modeled with IDM controllers with smaller min gaps, so that when you actually enroll them, they tend to tailgate more as they actually do in the real data. And you can now optimize these parameters over an entire city. So for all the training data for Boston, what is the best set of parameters? You can do this for a particular law. You can even do it for particular agents. So it could be that certain people in Boston, this particular person you observed was driving really aggressively, or this particular person was driving really timidly. You can just fit that. So once you have this data that's fit to these control parameters that are fit to every example, the claim is that you can now, in a model predictive control setup, unroll that logic. When you internally unroll, how do I think the world's going to evolve? Well, because I know I'm in Boston, I'm going to make sure that all the other agents use a small min gap, because I know Boston drivers tend to tailgate. And so what I'm showing here is this is the ego agent moving over time, and both of these were initialized to the same initial state. But what happened is this is the internal model of how the ego agent thinking world's going to evolve. If I endow all my other agents with Boston logic, they follow each other really closely because they have small min gaps. But if I give them normal min gap logic, they don't follow each other closely. So the idea is that I can just do the same model of control. Let me unroll how I think the world's going to evolve and then plan accordingly. But the problem though is, how do I know what control parameters to use? So one simple answer is that if I know that I'm in Boston, let me use my Boston control parameters. And actually that works pretty well. It turns out for the new plan competition, you're not allowed to know what city you're in, just given a little history of data you have to go plan. And furthermore, I also argued that not all Boston drivers tailgate. So certain people might not. So what we do instead is we train a classifier to predict the IDM parameters of each agent given its history. So essentially the intuition is that over the past, I think to some degree you might do this when you drive. You look over the past couple of seconds of how people are driving, like, oh, this guy's a little aggressive over here, this guy's a little timid. And so that I'm going to use, when I unroll in my head the world, my model of how the world's going to evolve, I'm going to say, oh, this guy's going to be timid, this guy's going to be aggressive. And I'm just going to use that mental model to then optimize for my trajectory. So essentially the trick is we take very similar architectures for predicting future agent trajectories, but instead of actually predicting X, Y, Z locations in the future, we predict parameters of controller, the parameters of an IBM controller. We predict what is the min gap that this guy is going to use. And once we use this, we just use that unrolled model in this model as a control algorithm. And so here's some visuals of, if we try to take all this data from our training set and we fit these parameters, this is sort of TSNE. So what we generally do find is that a lot of behaviors, IDM parameters are fit per city. So Vegas tends to have one set of parameters, Boston tends to have others, but there is overlap. Some individual logs and some individual agents, even in some Boston driver is timid, and maybe behaves more like a Las Vegas driver. I'll say this for a moment. And so basically the end conclusion is that we can do a form of model with control where we make predictions about how these agents will behave, and we can reduce error by a fair amount. So one thing to note is that once we get to, so C3 is this final metric, I think the real big take home metric when you evaluate the world in the simulator. And we only have, there's 100%, this is upper bound performance, so we only have 6% error, and we can reduce that to 4% by using these adaptive behavior models. And we can ask a slight variation as well. So what happens if we had ground truth behaviors? What happens if someone told us you're in Boston, use the Boston behavior? Or if someone even told us this driver is aggressive, this driver is timid, use a particular min gap here, min gap there. And you get slightly better. So what we're actually saying is that you can actually predict with fairly high accuracy the aggressiveness of individual drivers, these control parameters. Even if you have the ground truth, you don't get that much better. Here's some sort of fun examples of this in action. So here's our ego agents moving down. And then if you do the traditional model predictive control, you'll see this in a sample when it comes back again. You end up running into the car in front of you right here. There's a collision. But here, by better modeling the individual aggressiveness or passiveness of each agent in this log, you end up selecting a better plan that forces you to slow down and avoid hitting the car in front. There's other examples of the law. There's also examples of by better modeling the other agents around you and then predicting a plan as a result of that, you can much quicker get to your goal waypoint. Because it's a green dot. And you can do sort of fun things where you can train these behavior models on all cities but one, and say if you just train on 3 cities, how well do you do on a never before seen city? Because it seems like some of these behaviors are city specific. Turns out you don't lose that much either. You still see a win. So essentially, it seems like this notion of predicting control parameters for behaviors is an effective way of performing model control. Okay, so maybe I'll sort of kind of summarize here. So the take-home message here of like how do we sort of towards a pathway for full foundational robotics for self-driving. One bet that I would make is that understanding how the world evolves is going to be a first-class goal. So building 4D models of how the world is spatially structured and how that spatial structure evolves over time. And we can do it using these sort of self-supervised tasks where we model occupancy explicitly. And in order to model occupancy explicitly, we can even do a bit better by modeling the individual properties of the sensor, including the fact that it revolves. And that allows us to build even better models of geometry and occupancy. And given all these models, if we really understand how things can move and change over time, then one way we can incorporate them into final algorithms for autonomy is we put them inside model predictive control algorithms. And now we can use very smart estimates of how we think the world can evolve and how we build these behaviors. And this actually translates to improve performance on some benchmarks. We'll call it this.
Okay. Any questions?
Yes.
And then for the last PC controls,
Yeah.
you mentioned the IBM strategy is mostly the best with the few new.
Yeah.
But that was more about like following the lane. What about like lane changes and lane cutting? That also embedded in the IBM or not? Like because you don't drive straight all the time.
Yeah. So the way that the IDM logic works is that it needs a reference path. And so, okay, so there's 2 versions of the IDM. So if you have access to truth features of other objects, so when you run this as a simulator, you can actually look at those, like cars transfer lanes. And so what the IDM logic does is it will follow the pathway of the car acts. If it changes lanes, it's going to change lanes, but it will still do it with sort of this automatic. It's going to look for things in front and avoid hitting it. This is logic used for the reactive metric. Does that make sense? Okay. Now there's another question of, okay, that's the metric. But how do I do the internal world model to control? So there, I need to figure out, what is the reference? Yeah, because the IDM is not that fancy. It's just following a path and making sure not to hit something in front of it. So the way you get the reference path is actually, Arun, do you have an answer for that? How do you get the reference path to the other agents?
So there we put like a constant velocity.
Got it. Yeah, that's what I think that answered it. So there, for the other agents, we don't model them as lanes, at least for the internal world model. We're just saying you're going to keep going as your constant velocity, but we at least make those other agents smart enough where they'll slow down if something's in front of them. So you're right. We're still not really having that rich of an internal world model. And so I guess one more of the story here is it actually feels like model control is a nice setup, and it is kind of a workhorse for autonomy. And basically putting just more smarts into how the world can evolve is actually seamless. So with the original work that the PDMC did is just, it made those agents not reactive at all. They just move forward with constant velocity. So all we're saying is, okay, you can do that, but then make them so they don't run into stuff in front of it. And that by itself gives you a win. Just gives you even more. If we can actually understand, this agent feels like they're going to turn into this. And so I think that's where it's kind of linked to this first 2 pieces of work and how things evolve, how people behave. Then that I think models for model fit control. But right now, I think the thing that's limiting us is almost the general theme of machine learning these days is scale. Like we don't really have high quality behavioral data sets that are annotated. And so that's why the bet that I want to make is we can kind of self-annotate. We still don't have a lot of data. We definitely don't LiDAR sweeps like we have trillions of words. But we have about 2 orders of magnitude, 3 orders of magnitude less than that. But at least that data we still don't have fully. I think we can by applying these like 4D models. Yeah. Yeah.
And regarding the 4D foundation model, the serial model is well, like that's
Yeah, that's a great point. So importantly, class agnostic. But the way to think about it is that it's in the data. So I'm hoping classes might emerge in the same way that if you just train next word token prediction, incredible stuff seems to emerge. If we're just trying to predict where things will be in the future, in the data, I think it's true that smaller things don't move as fast. They tend to be people faster. So it could be that somehow in the learned model, it's internally reasoning about some sort of emergent semantics. But I clearly don't have look at that.
So have you tried like different situations, like indoor dynamic situation?
Yeah, that's
and
a,
the outdoor.
oh, that's a great thought. So the thing that we haven't done really is train this at scale. Because even though I try to advocate, okay, the labels are what's limiting us, so we can kind of self-label by fitting 4D models. But in reality, I think the data is limiting us. So right now, in terms of publicly accepted data, if I was still working at a self-driving company, this is what I would want to do. I would say, give me all, which we don't have annotation. I just want to fit models of how everything is moving. That is going to allow stuff to emerge about how people do move and behave. I don't know if you guys are interested, we should
Yeah.
try to do it.
I can have a follow-up question.
Sure.
Did you try like predict the color light point?
Interesting. Yeah, because you do have some reflectivity from LiDAR.
Yeah.
Yeah, that's a great thought. We have not, but I think that makes a lot of sense. If it's another signal, so why not, let the model try to fit to it?
Yeah, you have image and maybe we can predict the future images or we can predict the color of the light point color.
Oh, I see. When you say color, you mean RGB.
Yeah.
Yeah. I mean, that was like this. I showed a little bit of that with this kind of cute example of this dog. That was color plus LiDAR.
Okay.
And then it's your phone has technically this is LiDAR plus an RGB camera.
Okay, cool. Maybe
Yeah.
final question?
Okay, so I guess real world with like solid objects, whatever.
Yeah.
I was kind of wondering like what you would think about like, okay, let's say you have a robot that has like a very set of like sensory inputs that like you don't really like have like a real representation of. But then it's continuous somehow. So from that, like I predict what all these kinds of different what is it? I guess like what's it called? Inputs are gonna end up becoming. Do you think like work the same way, or is there like a kind of a need for this to something that's physical?
Yeah, I mean the claim. I go back to the kind of the quote from Pearl. Model the world, not the data. So of course the world is physical. It's undeniable. There's 3D structure, and as I move and as we move around the room, that 3D structure is evolving. So no matter how we sense it, be it tactile or radar or LiDAR or RGB, the world is the world. So I wanted it. Moral is that it feels like there's a win to be had in trying to abstract that away, the sensing of the world from the actual physical world. Because now you can generalize, maybe train on more scenarios. Yeah.
Okay. Final question.
So I assume you want to make a similar validation and for the training.
Yeah.
So do you think like 4D reconstruction is most important part to make a simulator, or do you think other parts of the system?
So it seems like in the context of what would it take to make a real photorealistic simulator of the world? great view synthesis results, nerves, and you go to all these workshops like multi-use. The thing that we don't really understand is behavior, like how things change over time. And I think it's because we don't have data. And so that would be my bet, is it's almost like the behavioral aspect of it, it's a real thing that's lacking. And the best take I would have on that is like, let's start by trying to scale on that. Because the scale seems to be profoundly important.
So how can you be?
Yeah, so I mean, that was sort of the philosophy of, okay, well, first, let's try to self-label. Requiring, at least, right now, if we only train behavior models from annotated data, that already restricts ourselves immensely. If we can learn from unannotated data by self-label, several orders of magnitude of data. That's probably still not enough. I'm saying like that's still nowhere close to what the language word people learn on. But one benefit we do have is that the data that we do have is way more. Like the 3D points are incredibly, like I think they're even more structured than images. So go to trillion scale to get reliable models of how. But that's a hypothesis. I think we just clear that up.
But I think like the company already have scalable data. So,
Yeah, you're right. You're right. So yeah, I was on the walls of a company. I would want to do. This is what I would do. I would say do self-supervised learning, try to self-label all that data, and then try to learn large-scale behavioral models.
Okay.